In this lecture, we're going to talk about dissolving metal reductions. The two dissolving metal reductions we're going to talk about are formation of trans alkenes from alkynes and the Birch reduction. You can see here that we can take an alkyne and reduce it to a trans alkene. Currently, the only other method we know of reducing alkynes is using H2 and Lindlar's catalyst. And this actually gives us the cis alkene. So a method to get to the trans alkene is quite useful. In this reaction, we use sodium and we use liquid ammonia, and this reaction is run at very cold temperatures. Sodium is highly reactive. Don't try this at home, but it is quite explosive when you mix it with water. We're more familiar with sodium in the cation form. Sodium metal can give us a free radical. Here's another example of reduction of an alkyne to a trans alkene. In this case, we're using lithium metal. So you can use either sodium metal or lithium metal in these types of reactions. And this shows us how sodium in liquid ammonia reacts to form sodium cation and a free electron. This is the radical species that is going to be critical to our reaction mechanism. Let's draw this out. Sodium metal gives you this free radical that can add to our alkyne. That alkyne then is going to split with one electron going to the right carbon and one electron going to the left carbon. What this does is gives you a radical on the left side and an anion on the right side. So this is the radical here and the anion there. This intermediate is known as the radical anion. And what you have, interestingly, in this intermediate is freedom of rotation. The molecule prefers to put those largest groups as far apart as possible, so it'll rotate so that way those two groups are furthest apart. In solution, then, we need to find a proton. The only proton floating around is from ammonia. And of course, this is horrible, and we would never ever use NH2 as a leaving group because it's a very strong base. But in this case, we're in such a strongly basic solution that it's allowed in the mechanism. So we added our first hydrogen on, and now we have a radical species. Sodium comes in again, so this is our second equivalent of sodium to form another anion. We have another equivalent of ammonia come in and protonate to give the product shown. The mechanism in your textbook shows a slight variation from the mechanism that I did. You'll see that it shows the solvated electron reacting. I prefer to show the sodium donating the electron. Either way is totally fine. This is our radical addition to an alkyne, where the solvated electron adds to the alkyne. Two electrons go to the right to form the anion, and one electron goes to the left to form the radical. The radical anion then has freedom of rotation to rotate the two largest groups to be farthest apart. We then have the proton transfer step where it picks up a hydrogen from ammonia, another electron from another equivalent of sodium, then comes in to our radical to convert it to an anion. This is a radical coupling step. And finally, we have one last proton transfer step from another equivalent of ammonia to get to the trans alkene. So we've said that the trans product is favored, and this is just showing you that in a little bit more detail. This is the radical anion species, and these R groups are the two carbon chains. And it's showing here that when they're in that cis orientation, you're going to have steric repulsion or steric strain, and this is going to be much less stable. So the more stable situation is when those two larger groups are trans, which is going to lead to our trans product. The Birch reduction is similar in that we are going to use a radical from lithium metal. Interestingly, this is one of the few ways that we can get our benzene rings to be reduced. Benzene rings, of course, are highly stable, and most reductions that we try to do aren't going to touch our benzene ring. The Birch reduction with these harsh conditions, again, you can see we're using lithium and ammonia, and we're going to get this 1,4-diene selectively, and we'll go over that in the mechanism. So lithium comes in and adds an electron. The pi bond then splits, with one electron going to the left to form an anion, and one electron going to the right to form the radical. So again, we have a radical anion. Next, we have a proton transfer step. In this case, the most acidic species is T-butanol. Addition of another radical from another equivalent of lithium is going to give us an anion. Resonance then brings that negative charge down. And we have one final proton transfer using T-butanol. Which leads to the 1,4-diene. This is the mechanism shown in your textbook. Again, it's showing the solvated electron doing the radical addition to the alkene. This forms the radical anion species. A proton transfer then occurs. Remember that our alcohol in this particular reaction was T-butanol. Another solvated electron from another equivalent from lithium comes in a radical coupling reaction to give our anion. After resonance and proton transfer, we get to the 1,4 substituted diene. Now let's take a minute to look at these resonance structures to understand why we get the 1,4 substituted diene. The anion that we formed has two resonance structures, and the one that is most stable is considered to be structure Y here. If you're trying to think about why that is, don't forget that there is a hydrogen in here. So that means that top carbon is sp3 hybridized. The negative charge in the anion is going to be repelled by the electron density in that sp3 hybridized carbon. sp3 hybridized carbons are great at stabilizing cations, but they have exactly the opposite effect at anions. You have all these nearby carbon-hydrogen bonds, and those are electron rich, and so the negative charge wants to move as far away from that electron rich carbon as possible. This concludes chapter 25. Please make sure that you review all of the points in the study guide for this lecture and let me know if you have any questions.